Okay, today I want to tell you about the Fourier transform. So we already started this yesterday, and what we are doing, we are studying the following equation. Uh, so in this equation, well, let me write it like this. Uh, in this equation, Laplacian of u of x was u of x minus 1 minus 2 u of x plus u of x plus 1. And we were interested in inversion of this operator. So green function was the matrix element of the inverse of this operator. So by definition. And we want to ask who this green function is. Oh, and in order to do this, we notice that our operator can be written as uh, 2 plus alpha times identity operator minus shift operator inverse, where the shift operator is defined in the following way. The shift operator can function x equals f of x plus 1. So, so the shift operator is given by this matrix. And its inverse is given by transpose matrix. So, in order to diagonalize, in order to compute the inverse for this operator, we want to first diagonalize it and then invert everything. So, and to diagonalize it, we need to find the eigenfunctions of the shift operator. And the solution to this problem is the following: that our functions phi k of x equal to 1 over square root of n e to the 2 pi I kx over n. So, and this k or k over n is called momentum, and this is coordinate. So eigenvalues of the shift operator acting on these functions are e to the 2 pi I k over n. So t phi k of t phi k equals to e to the 2 pi I k over n phi k. So the whole operator also acts with a function of k. So we alpha minus delta acting on phi k is 2 plus alpha minus e to the 2 pi I k over n minus e to the 2 pi I k over n minus 2 pi I k over n. So it's also eigenfunctions for the operator of our interest. And okay, so how shall we pass from coordinate to momentum representation? So when we sit in the coordinate representation, e to the 2 pi I k over n. So you can compute it from here. Let's shift x by 1, and it gives the overall factor. So so when we live in the coordinate representation, we can expand the function f or u, no, let it be f, in the basis of delta chronicles. So we can write that function of x is equal to the sum from x prime from 1 to n. So it like this. F of x prime, delta chronicle of x x and x prime. So we can expand any function in a basis of a function that equal to 1 only at one point and 0 everywhere else. But equivalently, we can use a different basis. We can write a momentum representation of the same function. So f of x is sum over k from 1 to n. F tilde of k 1 over square root of n. Maybe let me think. Yeah, let it be 1 over. Yeah, let it be 1 over square root of n here. So x dependence appears only in this exponential. We are taking these basis functions with coefficients equal to f tilde of k. And this transformation between f of x and f tilde of k, this change of basis, is called for the Fourier transform. So we have circularly ordered coordinates from 1 to n. well, this is x. And we have a circularly ordered momenta, k, which, which also leave so this mapping from momentum to the eigenvalue literally places this set of momenta on the complex plane, on the unit circle. So, so you can imagine that these points are eigenvalues of the shift operator actually on the basis functions. And so moreover, we can say that there is an additive structure on this and this sets. In essence, it is obvious. You can take two exponentials and multiply them and get a new exponential with value equal to sum of case. And everything is defined modulo n. So there are two abelian groups, z over n times z, and no, the same group. So and this mapping between such abelian groups is called Pendragon duality. So other examples of this duality which you'll see will be the following. Pendragon. So the same Pendragon is Pendragon classes. This is n. So other examples of this duality will be the following. So if one of these groups is a group of integer numbers, then its counterpart will be S1 with additive structure. It's the same as U1. And if this group is a group of real numbers, then this group is also a group of real numbers. So we will see this case and this case a little bit later. But I'm saying that there is a generalization of this Fourier transform, of course, to other cases, to functions on the line, on the lattice. Yeah, but so far, this Fourier transform is just a change of coordinates in the space of functions on endpoints. So now we can ask the following question. Well, what is the inverse Fourier transform? Yes. So we will check on this. Oh, yes, the answer is precisely this, that f tilde of k is equal to sum from k equals x equal to 1 to n, 1 over square root of n, f of x e to the minus 2 pi I kx over n. now we need to check why it is true. So we need to take uh, this definition of f tilde k and to check that if we substitute it into this formula, then we get our function of x back. So so sum from k equals to 1 to n f tilde of k 1 over square root of n e to the 2 pi I kx over n. Maybe what is better to do? And maybe let us say it the following way. We have this conjectural formula which we need to check. So we need to check that if we substitute this as a definition of f tilde k, then this formula gives this f tilde k back. So let us say that we start from this formula, from x equals to 1 to n e to the minus 2 pi kx over n. So now substitute here. So we want to check this. Now substitute here f of x. Change this index of summation to avoid the collision. Turn off k prime. So, and the only place where x enter this formula are these 2 points. So we can first compute the sum in x. So we have the following sum. And 1 over n. So what happens essentially? We applied 2 transformations to linear maps described by this matrix elements and this matrix elements, and we obtained the matrix element of their product. This matrix element is, so we can denote this as I of x prime. Yeah, so sorry, k prime. And this matrix element is summed with the function f tilde. So it is essentially a matrix product between, better to say, it's a product between a matrix and a vector, I and f. And we need to find this matrix. we need to find its matrix elements. So there are two cases. When k equals to k prime, what is the value of this I? Mm-hmm. No, why 1 over n?
Oh, if you leave it n out.
Hmm?
Because the exponential, the argument 0,
Yes.
and then you multiply by 1 over n.
Yeah, but you have n such exponentials.
Oh, you want the sum? I thought you wanted a matrix element.
No, the matrix element is a function of k and k prime, and it's given by the sum. So what is written here is a matrix product between two matrices. One with such matrix elements, another with such matrix elements. Yes. So it's 1, right? And second, if k is different from k prime, can you tell immediately what it equals to?
So an integral of e to the 2 pi
Hmm?
I.
Could you say it again? So k and k prime are from 1 to n, or you can think of them as numbers defined modulo n. But in this case, this inequality means that they are not equal modulo n. So there are two ways to understand what happens. The first way is to draw a picture. No. So the answer is 0, but we need to explain this. So one explanation why it is 0 is the following, that we have some root of unity, some nth root of unity, and this root of unity is repeated n times. So depending on whether this root of unity is primary or not, in a sense, it can be smaller root of unity. You get some picture like this. We get sum of complex numbers distributed over the so there is also this number. So there are numbers distributed, equally distributed over the unit circle. And since this picture has a rotational symmetry, we can rotate it by...
It's sum of all the unit of the root, the root of the unit times e to the 2 pi I k prime minus k divided by n. So it's 0 times something.
Yes, it's 0, because it is symmetric. It cannot have any other values. And another calculation that does essentially the same is the following. So we need to compute sum from x equal to 1 to n e to the 2 pi I kx over n, essentially, when k is non-zero. So it is a geometric progression, and it can be computed as so from 1, maybe, oh, it's fine, 2 pi I k over n. So the only requirement is that it is non-zero. To the 2 pi I k over n minus e to the 2 pi I k n plus 1 over n. Well, these two numbers cancel, because it is different by e to the 2 pi I. So, and this computation is important because we will have something of this kind in the continuous case. You need to compute this kind of sums and integrals using very similar methods. So in this case, this I of k prime equals to 0. So we can conclude that I of k prime equals to delta k and k prime. Maybe we can add this here. So, and since it equals to delta Kronecker of k prime, then the only surviving term, what will be the only surviving term in this sum?
Okay.
Yes, f tilde of k. So, is it okay? And what all this means in terms of matrices? We can write a matrix omega of xy is 1 over square root of n e to the 2 pi I x y over n. So omega is 1 over square root of n e to the 2 pi I. It would be better to sum from 0, but it doesn't matter. In this case, n plays a role of 0. So 2 pi I over n and so on e to the so the last is 1. Is it? So it contains the unit elements in the last row and last column. So there is this matrix and there is complex conjugate to this matrix. Mm. So this can be called a matrix of the Fourier transform. And there is complex conjugate in this matrix. Minus 2 pi x1 y over n. And so the statement is that these two matrices are mutually inverse. Omega star equals to 1. Good. Okay. Let us now talk about properties of this Fourier transform. First of all, let us notice that we started from real functions. Of course, we could consider something complex from the beginning, but if this function is real, then its Fourier components become complex, but complex with some properties. And let's study studying this question. So f of x, a complex conjugate is f of x. Let us write this condition for its Fourier transform. It's a reality condition, and let's compute complex conjugate of this. So it equals to so there is one problem that so if you want to compare this to sums, the range of this exponential is slightly different. In a sense, they are all roots of unity, but we need to rearrange them somehow. Mm. We need to perform some change of summation index. Mm. So let me think about this change. Let us say that k k equals to k.
Sorry.
Hmm?
What do you intend with the star of the f of x? Is like the complex conjugate?
Yes, of course. So, uh, I mean that we start from the real function. Yes, and want to ask what this reality condition means for its Fourier components. Hmm. So, this case goes from 1 to n, and let us introduce another k prime. Mm, Probably, or maybe let us define as n minus k. Maybe it's not sufficient in k prime. Yeah, probably yes. Mm, mm-hmm. Yes. Thanks. And then it's written as a sum from k prime equals to 1 to n, f tilde of n plus 1 minus k prime, 1 over square root of n, e to the it is still don't like how it looks. Mm. Hmm? Hmm?
if we substitute this, we get a minus a plus
Hmm.
for a tilde, and the rest becomes e to the minus 2 pi I k prime over n.
I don't like the fact that we get an extra exponential here. Hmm. Because this is multiplied by x. Yeah. And I would like to compare the exponentials alone. Hmm.
So x is real.
Hmm?
X is real or is
No, x is an integer. So, the problem is with this minus 2 pi x over n. What I'm actually trying to do is to realize this cyclic group by particular representatives in integer numbers from 1 to n. And maybe it's not a very good thing to do. Maybe it's better to write everything modulo n. Mm, so let me think. Mm. No, actually, it should be done like this. We should write the new coordinate that goes from that is defined as n minus k prime. Yeah. So a summation in this new coordinate k prime goes uh, from 0 mm, to n minus 1. Mm. Of tilde of mm, n minus k prime 1 over square root of n. So on here we simply change a sign in the exponential. So it is e to the 2 pi I k prime x over n. And then we compare terms of this expansion with this expansion. So for all k primes in this range, we have that f tilde was yes, so was no this f f has star. Yeah. Hmm?
I don't understand how substituting to k n minus k prime we get this.
We simply replaced the summation index first, and second, we neglected another exponential that was e to the minus 2 pi I n x over n. So this equals to 1. Yeah. Yes. So we compare these two expressions and conclude that f tilde of n minus k star equals to f tilde of k. It's for k from 1 to n minus 1. And there is one last term where k prime equals to also where k prime equals to 0. So in this case, we get a constant exponential. So it is a constant function, and we have its counterpart here, also for k equals to n. So k prime equals to 0 corresponds to k equals to n. So f tilde of n star equals to f of n. So it is a real Fourier component. So if I draw this picture, then it is k equals to 1, 2, 3. There is a function n. There is number n. So this Fourier mode corresponds to a constant function. And this complex conjugation corresponds to such a reflection of this set of points with respect to a vertical line. So this Fourier modes should be complex conjugate to each other. And also, depending on the parity of n, we can either have or don't have point n over 2, where this mode is real again. Can be either two mutually conjugated modes or one real mode. So there are these reality conditions. So if we use the modern notation, we can rewrite this equivalently that f tilde of k equals to f tilde of k k prime if k equals to minus k prime modulo n. So this is the general way to write this reality condition, which generalizes to all other situations. Yeah. So it was one property. Are there any questions?
I believe if we have this condition model, then the function is also real.
Yes, of course, because we are simply computing a complex conjugate of a function, and if you have this relation, oh, sorry, I forgot to put a star somewhere. Well, if you compute a complex conjugate and use this identity, then we immediately see that this complex conjugate is equal to the original function. So, it's some way to check whether you computed the Fourier transform correctly. So another property is about scalar product. We can define the scalar product on the space of functions in the following way. F times g equals to sum from x equal to 1 to n uh, f of x complex conjugate g of x. And let us ask what this means for if you write our functions in Fourier basis. So let us substitute the Fourier transforms here. So let us take this prefactor way. One sum for the conjugate function and another sum, k prime, for example. Sorry, this is g tilde, f tilde and g tilde. Sorry, not here. Yes, so it is simply by definition. And question to audience: is there anything in the sum that we can compute immediately? Well, there is a triple sum, and of course the summations in k and k prime cannot be done because they depend on functions. But can anything be computed explicitly?
These three sums are not one into another.
Hmm?
The second and third one are like, right?
Yes. So, yes, it might be ambiguous. But, so this all can be written as a triple sum. Or simply combine everything. Hmm? Yes, yes, yes. So we have this sum in x, and the only x dependence of this expression under the sum is the exponential. So the sum can be computed. It gives sum from k equals to 1 to n, sum from k prime equals to 1 to n, delta k prime, f of k, f tilde star g of k prime. So after all, it gives sum from 1 to n of tilde of k star g tilde of k. So we have recovered essentially the same formula as in the coordinate space. So we can formally write that it equals to f tilde uh, f tilde multiplied by g tilde. So the Fourier transform in the unitary transformation. So oh. And we could actually see this even at this stage, because omega star is omega inverse, but we also notice that omega transpose equals to omega. So omega star transposed, which is omega Hermitian conjugate, equals to omega inverse. So it's means unitarity. Okay, so shall we make a short break? 5. Hmm?
It is better if we finish
Okay.
before.
Mm-hmm. Yes. And then you have another lecture. It,
Yes, we have another hour.
ah, okay, so let's continue. So it was a so why we're doing all this? We wanted to compute the grain function. Uh, we can write all this in terms of matrices, but we can also uh, 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 let me think how to do it better. Mm. So we want to take the operator 1 over alpha minus O plus and act with it on a function f. Mm. So to do this, we can expand this function in the Fourier basis. So it acts in a variable x, and we know that each of these exponentials is the eigenfunction of the separator. So let us actually denote this expression written here as a lambda of k. So if you act with the separator, we need to divide by the eigenvalue of alpha minus delta. So it gives sum from k equals to n, from k equals 1 to n. Uh, mm, mm, 1 over lambda of k, f tilde of k. So for an image of our function is divided by lambda of k. And now we need to take the inverse transformation of this. So we want to write this as some kernel acting on f of x. So we substitute f tilde as a Fourier transform as the inverse Fourier transform. So it's sum from k equals to 1 to n, 1 over square root of n, e to the 2 1 over n, e to the 2 pi I k x over n 1 over lambda of k, e to the minus 2 pi I k x prime over n f of x prime, sum over x prime as well. So we can rearrange this a little bit in the following way. So it is, we can write it as sum from x prime equal to 1 to n g of x and x prime, f of x prime, so the formula for the g of x and x prime, which is actually a g of x minus x prime, is equal to what? What do you think? Just comparing these formulas. Mm-hmm. Mm-hmm. Yes, thanks. So we see that it is a kind of a Fourier transform of function 1 over lambda of k, but computed at the point x minus x prime, right? And this is an example of another property of the Fourier transform, which I would tell you. So this property, namely, it's a property that describes what happens with products of functions after the Fourier transform. So let me maybe erase this blackboard. So we have a multiplication structure on the space of functions. So it's not typical for the vector space. It's some additional operation, but we clearly have such an operation that we can take two functions and multiply them. So we know that there are functions f that correspond to Fourier image of Fourier image f tilde. There is a function g that corresponds to g tilde. And there is a product of two functions in coordinate space, and we would like to ask what it corresponds to after the Fourier transformation. So mm, uh, of course it corresponds to Fourier transformation of a product. There's no question about that. But I would like to express this in terms of Fourier transforms of f and g. So this operation was linear in nature of the terms. This relation should also be linear in both f tilde and g tilde. So, and we denote this relation by star, and this is called convolution. So we would like to find what this convolution is. So we are computing a Fourier transformation of product of two functions. And since we expect the answer as so this will be a function of k. And since we expect the answer in terms of their Fourier transforms, let us substitute these functions as their Fourier transforms from the very beginning. We first write that it is sum from x equals to 1 to n, 1 over square root of n, f of x, g of x, e to the minus 2 pi I kx over n. And then substitute each of these functions. K1, maybe k prime, one over n 3 half, f of k prime, g of k 2 primes, and then we have sorry, it's not k, it's x. Then we had this exponential at the very beginning. And then two exponentials, sorry, they are Fourier transforms. And there are two other exponentials, 2 pi I, k prime plus k 2 primes over n x. Oh, is it clear? Uh, so, and is there anything we could compute? Is there any sum that I computed? No, why two? We have just one exponential with some number multiplied by x. Yeah. So x is here, x is here. Yes. So delta function, maybe better to write it as delta function modulo n, in the sense that it is non-zero only when k prime plus k2 primes minus k is divisible by n. So let us write this as a sum from k, sum of k primes equals to 1 to n. We will write it as in this way, modulo n. So if I remove this delta function, this can be written as a sum of and also 1 over square root of n. So it is sum over k prime 1 to n f tilde of k prime 1 over square root of n g tilde of k minus k prime. I don't like this normalization of 1 over square root of n, but it appears, and probably it appears only in this case, because of such normalization. So we can define that it is a convolution of all the two functions. G star, G star, G tilde star, F tilde star, G tilde of k. So this is what convolution is. So in that case, we saw the inverse phenomenon that if some operator acts by multiplication by a function, then its action coordinate representation means taking convolution with the Fourier image of that function. So
When k minus k prime is minus and 0, it has to be intended mod n.
Yes, of course. So maybe I should have written this from the very beginning, but no, in some sense it's so in one sense it's easier to work with Z mod Zn. Um, some different sense it's better to work with integer numbers from 1 to n. No, but in any case, all these numbers should be mapped into either mapped to the fundamental domain or considered as numbers modulo n as elements of this group. Because here it's already impossible to write an explicit representative for each of this number, because we need to see who is greater than k minus n and so on. So better to think in this way. But we will not have this problem in in more complicated cases. Because, for example, if we live on the real line, then the convolution is simply f star g of x will be integral from minus to plus infinity. F of x g of so f of y g of x minus y dy.
But the fact that in the sum we have 1 over the square root of n shouldn't be, well, it doesn't seem to be symmetry between the sum and the integral because 1 over the square root of n doesn't become y, but
yes, it's true. When we pass to continuous case to integrals and sums, direct and inverse Fourier transform will become slightly non-symmetric. Well, they can be defined in a symmetric way by inserting square root of 2 pi, but it's not very good. And also, there is a difference between this discrete example and continuous example, because in discrete case, all the eigenfunctions were normalized by 1, and this was the meaning of this square root of n. But in the continuous case, it's impossible to do, because integral of any reasonable function of any reasonable exponential is infinity, so they should be normalized by delta functions. And this delta functional normalization produces some factors of 2 pi. So yeah, so this formula, this literal formulas don't have a nice limit, because if you want, for example, some of this kind, like this, to have a limit, you should insert here not 1 over square root of n, but 1 over n. Yes, something like. Yes, something like this. If you want the sum to converge to a integral.
and the relation between the function and the Fourier transforms tilde is what you call the Bloch inequality.
Well, Pontryagin duality is the relation between abelian groups, and the Fourier transform is a Fourier transform. So maybe let me write this formulas. Let me think what else we can do now. I mean, half an hour.
I think that we have a 10 minutes.
Okay. Okay, so let me give some announcement for the next lecture. So if you consider Fourier transform between a real line and a real line, then this transform in one direction is given by this formula: minus infinity to plus infinity. In dx e to the minus 2 pi, well, minus I px ikx f of x. In the opposite direction, it is f of x equals to decay over 2 pi. F tilde of k. So this is what I mean by a relation between R and R. And if it is if our original function was defined on a circle, then it corresponds to integer numbers, which means literally that f tildes are coefficients of the Fourier expansion of a function over the modes which are 2 pi periodic. So f tilde of n equals to the integral from 0 to 2 pi dx over 2 pi e to the minus I n x f of x and inverse transform to this one is f of x equals to sum over integers and maybe yes. So this is S1. We are integrating over S1, and here we are summing over Z. So let us. Are there any questions about this formulas? Let us try to check something with this case of Fourier transform on the real line. Probably I can erase this. So we define f tilde of k in this way, and we would like to check that f of x is given by that formula. So we want to compute integral from minus infinity to plus infinity, decay over pi e to the ikx e to the and the integral from minus infinity to plus infinity e to the minus iky and f of y. dy. So here again, we see some integral that that could naively be computed. So we have an integral in dy f of y times the integral from minus infinity to plus infinity in decay over 2 pi e to the I k x minus y. So see that this integral is not very well defined actually, because this function does not go to 0 at infinity. And I will justify all these actions the next time, but here they only want to compute this integral. And to do this, let us do the following trick, which is called regularization. So we can write that this is so this will be justified later, but we can write that this is a limit when epsilon goes to 0 of the following expression. Well, this part is the same, and here we write decay over 2 pi e to epsilon with 0 plus epsilon absolute value of k, the I k x minus y. So in this case, this integral is convergent. Yes. So let us call this expression delta epsilon of x minus y. And let's compute on this. So before computing this, I would like to ask you two questions. So the first question is the following. Do you know the value of this integral? Decay e to minus lambda k. And the second question is this.
The first is like 1 over lambda.
Mhm.
And the second,
Mhm. Yes. Because you are integrating positive function in each of the situations, the integrals converge. So what else can it be? So and here you have essentially this situation, but and lambda is epsilon modified by this x minus y. So delta epsilon of let us write it simply delta epsilon of x equals to to what? One integral is for positive case, and it is epsilon minus ix. Another integral is for negative k, so it is 1 over epsilon plus ix. And this is also multiplied by 1 over 2 pi. So if we combine everything together, then get 1 over 2 pi, 1 over pi epsilon over epsilon squared plus x squared. So we need to finish soon, right? Or yes. So I will only tell you a few properties of this function, and and one of them have to check at home. So first property is the value of this function at x equals to 0. So it's easy to see that it is 1 over pi epsilon. Then if you look at this function at something like square root of epsilon, sorry, delta epsilon of 0, delta epsilon of square root of epsilon is maybe better to take something even bigger, epsilon 1/3. So it behaves as epsilon to 1/3. So it goes to 0. And the last property that you need to check at home is that the integral from minus infinity to plus infinity of this function x so goes to 0 is 1. So combining these properties together, we can draw the following picture for this function. So it is something very high and narrow. So this size is something like 1 over epsilon, more or less. No, so it's something like epsilon. And its height is 1 over epsilon. And so, of course, the limit of such a function does not exist in the space of functions. They don't converge. It doesn't converge to anything point-wise. But we will see next time, and probably it's clear even now that its properties essentially repeat the properties of delta Kronecker. So the corollary of these properties will be that this equality can be continued, and it will equal to the value of a function f computed at point x. So this limit will equal to f of x. And we can say so far formally that a limit when epsilon goes to 0 plus of this so-called delta sequence delta epsilon of x minus y is a dark delta function of x minus y. So it's a generalization of delta Kronecker. And delta xy. Is the idea more or less clear? Like, so, okay. So, thanks for your attention. I will add some problems about this, and so next time we will study more about Fourier transform, about generalized functions. So we will just justify this computation and use it to green functions.